Hello, everyone watching me today. Today's session, we want to talk a little bit about the natural reward systems of the brain. And then we want to explore how these relate to addiction and drug use or use of drugs of abuse in wider society. So let's begin by talking about the natural reward system of the brain. Now, rewards can be defined as a positive effect that a condition or something has on an individual. And this positive effect is important because the positive effect then triggers motivation or incentive to continue the behavior. So this positive effect is generally considered a sense of pleasure. And that sense of pleasure that we feel is considered the reward. And therefore, because you experience that sense of pleasure, you're now willing to repeat the behavior. Now, let me give a very simple example. Many of us, there are certain foods that we don't like. When we eat that food, it doesn't give us a sense of pleasure. You know, we laugh and we joke, we talk about maybe vegetables like broccoli. In the Caribbean, in Trinidad and Tobago, there's a vegetable called karaili, which is very bitter. These don't produce that sense of pleasure. And therefore, the result is there's no motivation or incentive to eat them. On the converse, something that does produce a sense of pleasure, something like maybe chocolate cake, that gives a real sense of pleasure. And therefore you're motivated to repeat the behavior. Because of that, most of the things that produce a sense of pleasure, most of the stimuli that produce this sensation, these rewards, are generally essential for survival. So let's look at some of these examples. Well, let's start with some basic survival rewards. Thirsty. If you're feeling thirsty, the pleasure you get when you drink because you're thirsty. As we just said, the pleasure you get when you eat, when you're hungry. And of course, you can see the value of this, that if you didn't get a certain amount of pleasure when you were thirsty, then you might not be motivated to do it and you would end up dying. But humans are complex animals that live in social societies. And there are other things that also induce this sense of pleasure. Sex, important for reproduction, and love, they induce this sense of pleasure. Play, bonding, and spending time with family and empathy also are known to induce this sense of pleasure and are all now considered natural rewards. And so you can see that all of these things that we have identified do have an important component in survival of the species. Now, research has now shown that there are actual structures and pathways in the brain that are responsible for this reward system. These structures are linked into our sensory system, and therefore they're able to detect that which produces pleasure and then create the response that makes that pleasure experience occur within the animal or within the human. And the key structures inside of this pathway originate in the midbrain in a region called the ventral tegmental area. And then it passes to a region called the nucleus accumbens, and then moves on to the prefrontal cortex. And the fiber tract linking these structures is known as the medial forebrain bundle. So let me just repeat that. The pathway starts in the midbrain in the ventral tegmental area, moves on to the nucleus accumbens, and then onto the prefrontal cortex. And one of the major tracks linking these structures is the medial forebrain bundle. Collectively, this is known as the brain reward system, or sometimes it's referred to as the mesolimbic cortical system, because it links both the limbic system with the frontal cortex. Now, early research on this area noted a particular feature when this area was activated. This is research that was done in the 1950s, and you can see the reference for the original paper by Olds and Miller. In it, an animal, a rodent, was placed in a cage and an electrode was placed within this reward system of the brain. And that electrode was connected to a lever. And the animal would simply be moving around the cage exploring. And then by chance, it would press the lever. And when it pressed the lever, it would cause stimulation of the brain reward system. And therefore, the animal would get a sense of pleasure. Well, the animal would learn that pressing on the lever produces the sense of pleasure. And what happened then was that the animal would start to focus on pressing that lever. And then sometimes the animal would become obsessed and consumed with pressing the lever and ignored food and ignore water. So this sense of pleasure began to drive all the behavioral responses of the animal. It became so obvious that something was going on that some people considered it a model of addiction, which we're going to be talking about later. Now, research has been done on this particular pathway. And we now know that one of the key neurotransmitters involved in this pathway is the neurotransmitter dopamine. And often in popular literature, we see dopamine being referred to as a pleasure neurotransmitter. So this is just some graphs from real experiments that show that if you were to measure the levels of dopamine in parts of this pathway, when they're exposed to some of these natural rewards, you see that it goes up. So here you see measurements of dopamine in the nucleus accumbens when an animal has eaten. Prior to eating, the levels are fairly low. Once they eat, there's that spike indicating pleasure, and then it slowly goes down. And the same thing occurs with sex. And so now it's generally felt that part of the sense of pleasure that we experience is because of the release of dopamine within these natural reward pathways. Unfortunately, or fortunately for us, the brain is never as simple as that. And further research has shown that dopamine isn't so much just responsible for giving that sense of pleasure, but that release of dopamine actually serves as a prediction. It's a predictive factor. And dopamine is seeking to detect something called a reward prediction error. So this is a similar experiment in which we're measuring dopamine in the reward centers in the brain. And when a monkey receives some juice, you can see it gets a little spike of dopamine, indicating that that fruit juice, that sweet juice, produced a sense of pleasure. That dopamine, that juice, is now paired with a light signal. And the animal learns to predict that the light signal is going to mean the juice is coming. And what happens now is that the dopamine gets released at the point of prediction. And there's not much dopamine actually being released when the reward actually arrives. So the bigger spike of dopamine is to predict that a reward is arriving. After a while, if no reward is given, notice that there's actually a decrease in dopamine. So a reward is being expected, it does not arrive, and there's now a decrease in dopamine. And so all of this can now be said, and this has been repeated in human experiments, to say that the reward system is most activated when you get an unexpected reward. It's partially activated when you get an expected reward. And if a reward is expected, but it does not arrive, then there's actually a depression in the signal. And collectively, the brain is able to use this to predict what is going to happen. And this idea of prediction is very key for survival and allowing animals to grow and survive in nature. And so dopamine is key. And we continue to explore and seek to understand exactly what is the role of dopamine inside of this reward system. Okay, let's talk a little bit about drugs. Now, these are some basic principles about drugs that you probably know already. A drug is a substance that, on entering the body, can change its functioning or change some aspect of the body functioning. You have different classes of drugs based on how they interact with the receptors and the neurotransmitters in the body. So here we're talking about drugs that specifically affect the brains and receptor sites. Agonists are drugs that mimic the neurotransmitter. They give a response that is similar to the neurotransmitter. So a dopamine agonist will give a response that's similar to dopamine. Now they can do that in many different ways. One of the ways they can do that is to actually be of the same shape and size as dopamine and interface with the dopamine receptors. Another way is it can stop the enzymes that break down dopamine from working. And a third way is it can actually stop the reuptake of dopamine. So agonists can work in many different ways, but the key thing is they mimic the effect of the drugs. Antagonists are opposite. They block the effects of the drug. And in like manner, they can do this in many different ways. The primary one in which it is often done is by blocking the receptor sites or blocking the release of the neurotransmitter from the presynaptic terminal. Now, when talking about the brain, we often talk about psychoactive drugs. Now, psychoactive drugs are drugs that have psychological effects upon the brain. For example, they might produce hallucinations. You might see things or you might hear things. Or they can help relieve anxiety. These will all be examples of psychoactive drugs. Now, one of the things that has been discovered is that drugs of abuse, drugs such as cocaine, heroin, marijuana, these drugs of abuse all seem to powerfully activate the natural reward pathways in the brain. But they're not connected to any purpose. And therefore, this can lead to a corruption of the brain's reward mechanism. And over time, it can change behavior, leading to an addiction state. Let me say that again, and we'll look at some examples. Drugs of abuse, most of them have been shown to powerfully activate the natural reward system by increasing the levels of dopamine. However, if you use cocaine, that's not connected to any purpose of survival in life. And so this activation of the reward system that's not connected to survival purpose leads to corruption of why the system is there in the first place. And over time, if you keep engaging in that drug use, it corrupts the system and changes the way we respond to stimuli and behavioral patterns. And this, we believe, is part of the models of addiction. So here are clear examples from different experiments that show for all of these drugs, amphetamine, massive increase in dopamine in the reward pathway, the nucleus accumbens. Cocaine, very large increases. Nicotine from cigarettes, morphine, all of these drugs of abuse can act through various mechanisms to increase the amount of dopamine being released. And I want you to note the amounts that are being released by certain of these drugs. Many of these drugs can release amounts that are 300, 400, 500 times, 500% more than what's normally expected. How do these drugs do this? Well, there are various mechanisms by which this can be achieved. Certain drugs like cocaine and amphetamines, they increase the amount of dopamine by blocking the reuptake of dopamine back into the presynaptic terminal. As a result, more dopamine remains in the synaptic cleft, activating the natural reward pathway. Other drugs like nicotine and marijuana and morphine and other opioids, they act directly on specific receptors in the brain. So marijuana has what are called cannabinoid receptors in the brain, and it acts on these cannabinoid receptors. Nicotine acts on nicotinic receptors in the brain. morphine and other opioids act on specific receptors in the brain. And this then activates a change in the natural reward pathway, as we all see. And then there are a couple other drugs like alcohol and angel dust, PCP, that can also inhibit certain channels in the natural reward pathways and dysregulate them. So cocaine and amphetamines increase dopamine levels in the synapse by blocking reuptake. Nicotine stimulates presynaptic nicotine cholinergic receptors that lead to an increase in the release of dopamine at the nerve terminals. So on the presynaptic membrane, there are nicotinic receptors, and nicotine can act here to lead to a greater release of dopamine. Opiates like heroin and morphine, they inhibit GABAergic neurons that would normally suppress the dopaminergic neurons. So let me go back to our diagram here. So these are dopaminergic neurons, and the brain tightly regulates everything. And there are inhibitory GABAergic neurons, neurons that inhibit this pathway to help regulate it. And the morphine and other opioids inhibit those GABAergic neurons and allow this pathway to become more active, leading to an increase in dopamine. And so you see different drugs of abuse have different mechanisms, but they all seem to lead to an increase in the amount of dopamine. Finally, a couple of drugs of abuse don't directly involve dopaminergic effects. Alcohol seems to have non-specific effects on many neurons in the brain, blocking NMDA receptors, and so does angel dust. And so there are some other classes of drugs that we're seeking to understand. So we can summarize all of this, and this is just a parody. The smile here is not really meant to mean that it's a good state, but we can summarize by saying that normally the natural reward system is designed to give us an appropriate increase in pleasure. But when your brain gets exposed to drugs of abuse, you get too much of this pleasure response, and that can corrupt the system. So today, addiction is viewed as a brain disease. Now that's a fairly significant shift that has taken place. Because many years ago, I think addiction used to be viewed as a moral failing, people who didn't have self-control. But now many of us, well, not many of us, but within the field or the research community, they think that when you suffer from addiction, it's because something has gone wrong with these neurotransmitters and these different pathways. And I just want to talk a little bit about some of the features of addiction and then look at some of the other things that might be happening in the brain. Addiction is generally defined by having three components. First is called cravings, where you get a preoccupation with obtaining the drug. The second is intoxication, where you keep using the drug despite the adverse consequences that it causes. And then the third is withdrawal. When you stop using the drug, you get an negative emotional state, and that makes it very difficult to stop using the drug. Let's look at these and some of the brain changes taking place. Well, one of the things that seems to happen, especially with the dopamine response, is something called tolerance. Here you can see a person is exposed to 2 doses of dopamine. During the first response, you get a lot of dopamine being released. But during the second response, you get a much smaller release of dopamine. For some reason, the second exposure produces a much smaller release in dopamine. And this is called tolerance. The person becomes less responsive to the drug. And therefore, to keep getting that same initial dopamine response, they are required to take larger and larger amounts of the drug. And this seems to be something that happens to keep getting that sense of pleasure, that intense sense of pleasure that they might have experienced the first time you now have to take larger and larger amounts of the drug. And this can be very dangerous because you can then lead to levels of the drug that are toxic and can actually cause death. This particularly happens with the opioids like morphine and heroin. The exact mechanisms for tolerance are unclear, though we do believe it has something to do with receptor desensitization. One of the things that seems that might be responsible for this tolerance is that there's evidence to suggest that if you use these drugs over a long period of time, the dopamine signaling in these reward pathways changes because there are actually physical changes taking place in the cells, that they actually get smaller and actually begin to release less dopamine. This will not just have an effect on the response to the drugs of abuse. This actually has an effect upon the whole reward system. And when the person isn't getting those rewards, they can enter into an unrewarded or amotivational state. Something that's often seen with chronic marijuana use, where people develop amotivational syndrome and they're not motivated to engage in any productive behaviors. And part of the reason is believed is because of this physical shrinkage of the neurons. Again, these are just research findings that scientists are trying to put together to make sense of a very complex behavioral problem, which is addiction. So these cravings that people experience seem to be because the baseline levels of dopamine activity in the system actually decrease. There's tolerance to the previous dose and normal rewarding stimuli. And therefore, there's this sense of the need to get the drug. And very often, as we see, the paraphernalia, the things that predict the drug use are actually the ones that give a greater release of dopamine. And all of this can lead to cravings and people running after the drugs. Another thing that seems to happen is something called hypofrontality. Now, within the brain, we have the frontal cortex, consisting of the prefrontal cortex and the orbitofrontal cortex. And they seem to be very important for things like attention, regulating working memory, and also behavioral inhibition. This seems to be part of the brain that allows you to judge and weigh up options, and then inhibit behaviors that might be the result of activation of your emotional centers. And so something might happen and you might get very angry, and you might want to act out on that anger, but it's the prefrontal cortex, the frontal lobe, the orbital frontal cortex, that will allow you to make a decision and inhibit those responses that are coming from your emotional centers. During addiction, it seems that there's a shifting in the pathway, and the ability of the prefrontal cortex to function in that manner gets reduced. And that's why it's called hypofrontality, a reduction in the functioning of the frontal lobes. And the person moves towards impulsivity and compulsivity. So what's happening here is the effectiveness of natural rewards are not working. There's a desire for the drug, and there's a loss of the ability to regulate compulsive and impulsive behavior. And therefore, persons who are suffering from addiction, they then begin to make strange choices and strange decisions, predisposed on getting access to the drug. Finally, it's also been shown that when you stop taking the drug, that neurons in the amygdala get activated. And we know the amygdala is very important for activating the fear and the stress response. And it is this that we believe characterizes withdrawal. So when you stop using the drug, there's a massive release of corticotrophin releasing factor. The amygdala gets activated, and you enter into what's considered a chronic stress state with increased heart rate and increased blood pressure, and a general sense of unease and negative emotions, all of which are associated with withdrawal, and then may lead one to want to go back and take the drug. So all of these are just some insights into what could be taking place in the brain based on research, all pointing to the fact that maybe once people get addicted to these drugs of abuse, there's something that has gone wrong in the brain circuitry and brain chemistry. And if we can understand this better, maybe we can come up with interventions. So let's just talk a little bit about principles for intervention. Now, one of the first things we want to mention is there's a difference between how much pleasure the drug causes and how addictive it is. Some drugs can not cause as much pleasure, but they have a very addictive quality because they keep the person coming back for them. And the distinction here and why this occurs is still not well understood. So it seems like cocaine will lead to a lot more release of dopamine, but nicotine is as reinforcing, seems to be as addictive as cocaine, some studies have found. And so getting people to stop using cigarettes can be sometimes just as challenging as cocaine addiction. In terms of addiction, the treatment must always begin with a process of detoxification, helping the person navigate that withdrawal process. Depending on the drug, it can be a very mild experience or it can be very severe. Alcohol withdrawal can sometimes lead to hallucinations and fever and seizures that can be life-threatening if not managed by medical professionals. And so this process of withdrawal has to be managed by medical professionals for all drugs. In terms of pharmacological treatment, some of the things that have been tried have been the use of agonists, replacing drugs with similar drugs that can be reduced over time. So for example, in treating nicotine addiction, you now see we have a lot of nicotine gums and patches. In treating heroin addiction, sometimes in some countries they give out methadone. And the idea is that produces a less effect that can be reduced over time. You can also give drugs that block the effect of the drug of abuse. For example, to treat opioid addictions, you can give the drug naltrexone. And what that does is it blocks the pleasurable effect. So when you take the opioid, if you've taken the naltrexone, you won't feel the pleasure, you won't get the joy from it. And therefore, you might be less likely to take it. But of course, the idea here is unless you're very motivated, you won't actually take the antagonist. And so that's one of the challenges. One of the ways people are trying to get away from that is developing implants. And once it's been implanted in the body, it can stay there for several weeks or months. And so here you see two animals, rodents, that have been exposed to alcohol. One received an antagonist that blocks the effect of alcohol at the GABA-A receptor. And you can see that animal is fine and doing well. The other did not and has become intoxicated. And finally, they talk about aversive treatments. This is especially used in alcohol treatment sometimes, alcoholism, where you can give a drug that when you take the drug of abuse, it now triggers an aversive response. And the example here is something called antabuse. When you take alcohol, if you've taken antabuse before, it gives feelings of nausea and sickness and upset feelings. And therefore, the person now begins to associate the alcohol with not something pleasurable, but something negative, and may stop taking it. Of course, again, this requires high motivation on the individual to take the antabuse. And all kinds of interesting things are being tried, like drug vaccines, to give antibodies that break the drug down very quickly before it can affect the body. One of the key things to note about all these treatments that are being tried is generally they must work in conjunction with social support, counseling, and psychological therapy. None of these pharmacological treatments have been found to be very successful just by themselves. Okay, so that brings us to the end of today's session on drugs, addiction, and reward. Remember, one of the things we said when we started looking at this issue of behavioral neuroscience or physiological psychology is that the approach here is that every experience that a human has is because of changes in the brain. That's the theory. I'm not saying that's true. That some scientists believe that everything that we experience is because of changes in neurotransmitters in the brain. And here we've been able to explore that the sense of pleasure that many of us experience, that is because of a natural pleasure system in the brain called the brain's natural reward pathway. We were able to see that that pathway runs from the ventral tegmental area to the nucleus accumbens and onto the prefrontal cortex and involves the medial forebrain bundle. The key neurotransmitter in that pathway is dopamine. That's elevated when there's a sense of pleasure. And dopamine seems to serve as a reward prediction signal, tracking what rewards are coming your way. We saw also that the natural rewards that promote survival, like food and thirst and sex, lead to an increase in dopamine in these regions. And then we went on to look at models of addiction. And we saw that many of the drugs of abuse also lead to increases of dopamine in this system. And that when you take these drugs over a long period of time, it does lead to corruption and changes in the natural reward pathways that can lead to some of the signs and symptoms of addiction. The more we go forward and the more we can understand these things, is it better we might be able to offer people solutions to the challenges that they face. Take care.